Bismillahirrahmanirrahim. Assalamu alaikum. Dear students, I welcome you all this course on data communications and computer networks. This is our lecture number 4 of asynchronous mode of learning in phase 2. This course is being offered at Department of Computer Science, ComScience, University Islamabad, Lahore campus. So today we'll talk about resource allocation and congestion control. And we'll discuss the issues in resource allocations. Then we'll talk about queuing disciplines, first in, first out, fair queuing, and we will also be talking about active queuing management techniques. The learning outcomes of today's lectures are to understand the resource allocation mechanisms, and at the end of the lecture, we must be able to understand and critique different queuing algorithms. We should be able to investigate or understand the variants of congestion avoidance mechanism, their benefits. So let me quickly review what we discussed in the last class. In the last class, we talked about the TCP congestion control mechanisms. We discussed TCP, different variants of TCP, TCP Tahoe, TCP Reno, TCP New Reno, TCP selective acknowledgement, and obviously there are other variants as well, such as TCP Vegas, TCP Big, TCP Cubic, etc. And then we talked about the different TCP timers, such as retransmission timeout, and we discussed how retransmission timeout is calculated based on round trip time, and since the round trip time is not stable, is varying all the time, so we have to calculate an estimated RTT, and then we also need to modify the calculation of retransmission timeout by accommodating the variance in the sample RTT. And then we discuss other timers of the other timers that TCP makes use of, such as time-weighted timer, persistence timer, and keep alive timer. So today we will continue our discussion on TCP. We'll continue our discussion on congestion control. And we'll add resource allocation to it. Resource allocation. So remember, we have discussed the congestion control mechanisms in the last class. These are the end-to-end congestion control mechanisms by discussing different variants of TCP. But this discussion is incomplete until we discuss resource allocation as well, right? So resource allocation and congestion control are basically two sides of the same coin. So it's very important to complete our discussion on congestion control by discussing resource allocation mechanisms. So first of all, let us try to identify that what is the problem of resource allocation that we want to discuss. What do we think? What is the problem of resource allocations? The problem of resource allocation is that how to effectively and fairly allocate resources among a collection of competing users or nodes. All right, so two things are important that we'll be focusing throughout this lecture is how to effectively and fairly allocate resources. But let's talk about first, what do you mean by the resources, right? What sort of resources we are trying to allocate. So when I say resources, so this means I'm talking about bandwidth of links. And the buffers on the routers or switches. Why we are interested in allocating buffers on routers or switches? Because here we queue the packets for transmission. So the buffers on the routers and switches where packets are queued for awaiting transmission. Right. So we are interested in fairly and effectively allocating the bandwidth of links and the buffers on routers and switches. We are interested in this because packets contend at a router for the use of a link. What if there are too many packets? What if we have too many packets? What's the problem? Yes, if we have too many packets, so this means, number one, maybe packet experience increased end-to-end delay. So too many packets means maybe we end up having increased end-to-end delay, or the queue overflows and packets have to be dropped. Obviously, if you're sending too many packets, more than the queue of a router or a switch, the queue will overflow, and then we have to drop the packets. So this means queue overflows, and the packets have to be dropped. Right. So this is the problem managing the resources. But as we know, and we have discussed in the previous class, that most networks provide a congestion control mechanisms to deal with such a situation, right? Where we have, end-to-end delay, or where the queue overflows and packets have to be dropped. We have this congestion control mechanism to deal with such a problem. But remember, let me write it here. Remember that that congestion control and congestion control and resource allocation that we want to discuss today, and resource allocation are two sides of the same coin. Sides of the same coin. The purpose is to address this problem, means end-to-end delay, and if the packets are too much, how to make sure that packets are not dropped or dropped intelligently. And by the way, both these mechanisms, either we talk about this congestion control or resource allocation. Both these mechanisms involve host and network elements. So both involve, in both mechanisms, both involve hosts and users and network elements. Network elements such as routers, but let me elaborate a little bit this network element detail that we've already covered. That if we want to control congestion, the end hosts are involved. Where we have variety of congestion control mechanisms. The end host will monitor the network, identifying a packet loss or duplicate acknowledgement as a trigger of or as a congestion indication, right? And will slow down the sending rate. But what do you mean by the network elements? So when I say network elements, this means I'm talking about various queuing disciplines. Right? See, we have not covered this so far in terms of congestion control. So various queuing disciplines, we can use these various queuing disciplines. Various queuing disciplines can be used to control, control the order in which packets get transmitted, and we can also make a decision that which packets get dropped. Right. So why we are interested to take our discussion of congestion control to the network elements, because in network elements where we have various queuing disciplines that we can make use to control the packets at routers or switches. By saying control, we mean that we can decide which packets will get transmitted and which packets get dropped, right? So this is an important decision. So before we move on, so let's talk about what do you mean by queuing discipline. So when I say queuing discipline, this means a queuing discipline basically it segregates the traffic, right? So it segregates the traffic to keep one user's packet from unduly affecting another user's packet. So what it does is basically it segregates traffic. Why? It segregates traffic to keep one user's packet from unduly affecting the other user's packet. So that's why we are interested in. So we don't want one flow to affect the allocation of or the transmission of the other flow. That's why we want to discuss a queuing discipline or the queuing algorithms. So this resource allocation that we are interested in discussing is partially implemented in the routers, switches, and the link inside the network, and partially in the transport protocol running on the end host. So let me summarize this resource allocation problem. So what we'll be doing here, the resource allocation means that we are partially implementing this. We will be partially just partially implemented in the routers. Switches and links inside the network, and partially implemented in the transport protocol. Right? And obviously this transport protocol is running on the end host. So probably we have briefly covered this implementation of resource allocation in the, or implementation of congestion control in the transport protocol at the end machines. But so the focus would be on partially implementing resource allocation in switches, routers, and the links inside the network. Let's talk about the issues in resource allocation. So the next thing that before discussing any specific resource allocation mechanisms, let's talk about the issues in resource allocation. So in the issues in resource allocation, we'll first talk about the taxonomy of the number one point that we'll discuss here is the taxonomy of resource allocation mechanisms. Taxonomy of resource allocation mechanisms. Since the resource allocation mechanisms differ, creating a taxonomy is a very difficult proposition for the resource allocation mechanisms. But we can have these three different types of resource allocation mechanisms. Number one, router-centric versus host-centric. Router-centric versus host-centric. So what do you mean by router-centric? So when I say router-centric, this means when packets are forwarded and selecting which packets are dropped. So this means the decision when packets are forwarded and selecting which packets are dropped. Which packets are dropped. And what do you mean by this host-centric? By saying host-centric, this means host observe the network conditions and adjust the behavior accordingly. And by the way, we have covered this in typical congestion control mechanism of TCP that was host-centric, where a host was observing the network condition and adjust its behavior accordingly too. So in this case, host observe the network condition and obviously it adjusts its sending rate accordingly. But important thing that I want to note here is that these both mechanisms are not mutually exclusive. Right? These two groups of resource allocation mechanism, either a resource allocation mechanism is implemented at a router, means it's router centric, and or host centric. These are not mutually exclusive. These are pretty much related with each other. So these two groups, these two groups are not mutually exclusive. It's very important to remember this. Okay, so this is one type of or category in taxonomy of resource allocation mechanism. The second is reservation based. The second is reservation based versus feedback based. Okay, so what do you mean by this reservation based? So by saying reservation based, based means that each router allocates enough resources. So this means that each router allocates enough sources or resources. And what do you mean by these resources? These resources means that we are talking about the buffers and our the percentage of the link bandwidth. Percentage of the link's bandwidth. Okay, so all the resources mechanisms based on reservation is basically demanding from routers to allocate enough resources for a packet transmission. These resources include buffers or the percentage of the link bandwidth. And then we have the feedback-based resource allocation mechanisms. Feedback-based. And we are talking about the feedback. This means the feedback is either explicit or implicit. So either we are sending explicit feedback or implicit feedback. Okay, and then there is another category here, the taxonomy of resource allocation, and it's called window-based. Window-based versus rate-based. Okay, both these flow control and resource allocation mechanisms, the purpose is to tell the sender that how much data is allowed to be transmitted, right? So there is a there are two ways to tell the host that how much data it can send on the network. Either we can use a window-based mechanism or a rate-based mechanism, right? So window-based we have already covered in the typical TCP end-to-end congestion control mechanism. So what do you mean by this rate-based? By the way, so the window-based we have already discussed in detail that a sender maintains a window that is based on the receiver's feedback or receiver's congestion, receiver's buffer space, and how based on this information at the network condition, a sender controls the sending rate, right? So what do you mean by this rate-based? So the rate-based is basically more suitable for multimedia applications. Multimedia applications that we'll discuss in quality of services in the next class, inshallah. So the rate-based is for many different multimedia applications. Why? Because the multimedia application tend to generate data at some average rate and which needs at least some minimum throughput to be useful, right? So that's why if we are dealing with the multimedia applications, probably resource allocation mechanism can use this rate-based feedback mechanism to control the sending rate of an application, right? And why we are interested in this rate-based for multimedia application? This is because these multimedia applications want at least some minimum throughput to be useful. Okay. Before we move forward and talk about some of the evaluation criteria for the different resource allocation mechanisms, let's talk about different service models that are being used in the networks for congestion control at the moment. So there are two types of service models. So we want to talk about the service model. There are two types of service models. Number one is called best effort. To conclude this, the introduction or the problem of resource allocation mechanisms, let's talk about the service model. So one is called best effort service model. So by the way, this we have covered in details, right? The best effort service model of TCP. What it does is that it implies that feedback is being used, right? Means such a model does not allow user to reserve network capacity, and this was precisely happening in TCP's congestion control mechanism. So it implies that that the feedback is being used. And used for what? Used to control the sending rate of a sender or a node, or to control network congestion. Such a mechanism, of course, such a service model, does not allow users to reserve network capacity. Right, so this we have already covered. This type of service model is something that is used by TCP's end-to-end congestion control mechanism. And the second type of service model is called quality of service based service model. So this implies some form of reservation. So it implies some form of reservation, right? So it implies some form of reservation. This means what? This means this requires significant router involvement. This was not happening in our earlier discussion. We did not discuss any such mechanism where a router was involved in some sort of reservation. So this requires significant router involvement. What do you mean by this? This means router involvement such as queuing packets, queuing packets differently. Depending upon the level of the reserved resources, right? So so probably would more be interested in this quality of based service model when discussing the different resource allocation mechanisms. So before we talk about different resource allocation mechanisms, so let's talk about the evaluation criteria that we have to use to evaluate the effectiveness of any resource allocation mechanism. So before discussing any resource allocation mechanism, we are interested in looking at evaluation criteria. Evaluation criteria. Right. So as we discussed in the beginning, that the problem of resource allocation is that how a network effectively and fairly allocate its resources. So there are two broad measures that we'll be focusing in evaluating any of the resource allocation mechanisms. So there are two broad measures that we'll be keeping in mind. So two broad measures. Number one is called effective resource allocation. How effective is a resource allocation mechanism is. And number two is fair resource allocation. How fairly a resource allocation mechanism is managing the resources of resources in a network. So let's briefly talk about the first measure, and the first measure is effective resource allocation. So the first measure is effective resource allocation. All right. So when we talk about effective resource allocation, we consider two principal metrics of networking. So this effective resource allocation mechanism needs to consider two principal. It should be considering two principal metrics of networking. What do you think? What are these two principal metrics? Any guess? Yes, you're right. One is called throughput. And the other is delay. So, you know, we will when we talk about the effective resource allocation, so basically we are talking about how much throughput will be getting by using a resource allocation mechanism, and how much we have minimized the delay, right? So, but the problem here is, I mean, we want to maximize the throughput. We want to send as many packets as we would like in the network. But the problem here is, the problem with this strategy, where we want to send as much we want with a little delay, is so the problem here is increasing the number of packets, increasing the number of packets in the network also increases the length of the queue, also increases the length of queue. What's the problem with this? What will happen if we have increased the length of the queue at each router? This means a longer queue. A longer queue in turn means packets are delayed longer in the network. So this results in, what? This results in longer queues. And longer queues means what? This means packets are delayed in the network. Right. So obviously, the effective resource allocation mechanism is focusing on the two principal metrics of networking, that is to maximize throughput by sending as much packets as we want. But the problem with such a mechanism is that if we increase the number of the packets in the network, this means this will also increase the length of the queue in a router. So if the length of the queue in a router is increased, this means we will have longer queues. If a queue is longer, this means this means packets are delayed in the network. So that's why the important thing is to keep consideration, keep the ratio of throughput to delay into consideration for evaluating the effectiveness of a resource mechanism. So rather than only thinking about sending too many packets in the network, we would like to look at these two, or evaluate these two principal metrics of networking in terms of the ratio of throughput to delay. Is important. So it's important that we have this this ratio of throughput and, yes, you're right, delay. Right. So by the way, this ratio between throughput and delay is called power. So rather than only focusing on the throughput and sending too many packets in the network and then resulting into longer queues means the packets are delayed in the network, we want to keep this ratio into consideration in effective resource allocation mechanisms, and this is called power. This is called, in fact, power of the network. Power of the network. Right. So power of the network is a ratio basically between throughput and delay. And obviously, if we want to maximize the power, so what we have to do, yes, you're right, we have to minimize the delay, right? So this is an interesting, ratio that an effective resource allocation mechanism needs to consider. By the way, this was proposed by MM1 queuing network. And this network assumes infinite queues, right? So what this network assumes, there are infinite queues. I mean, there is no restriction on the queue length. But we know that if we want to use such a ratio in real networks, then real networks have some limitations. So if I talk about real network, in real networks we have finite queues, number one, and because the queues are finite, we will also drop packets when a queue is full. And then the other thing is we have multiple competing connections. So we have multiple competing connections to have the access of the resources. So the objective should be to maximize the ratio, right? So maximize this ratio, which is a function of how much load you place on the network. The load in turn is set by the resource allocation mechanism. So I would like to repeat this, right? So the objective of this effective resource allocation mechanism is to maximize this ratio of throughput and delay, which is a function of how much load you place on the network, and this load management is done by the effective resource or the resource allocation mechanism. Let's try to understand this with the help of this the power curve. So let's try to understand this with the help of this power curve. So here we have throughput and delay. The throughput and delay ratio, right? As a function of load, right? And let's assume that this is the power curve. Right, so this is the power curve that we are talking about. Okay, and let's assume that here is the optimal power. This means what? That a resource allocation mechanism would operate at the peak of this curve. So the resource allocation mechanism would operate at the peak of this curve. At the peak of this curve, this power curve. Right, but what if we are on the left of this optimal power or this peak? What if we are on the left of the peak? What do we mean by this? This means the mechanism is being too conservative, right? The resource allocation mechanism is. This means the mechanism is being too conservative. Means we are not sending enough packets in the network. And what if we are on the this side of right side of the curve? This means what? This means many packets allowed into the network that will increase delay. This means many packets allowed into the network. That would obviously increases delay. So keeping this for any effective resource allocation mechanism, it's very important that we keep the optimal power. This means we want a stable system. The purpose of this power curve is to come up with a stable system. Okay, so what do you mean by a stable system? It's very simple. A stable system is the one where packets continue to get through even when the network is operating under heavy load. Okay, this means packets continue to get through. They're not dropped even when the network is operating under heavy load. Right, so for that this optimal power or this ratio is very important, right? So that it's possible that a network may experience congestion collapse if a mechanism is not stable. It's a very important thing to understand, right? So if a resource allocation mechanism is not resulting into a stable network, this means we may come across or a network may experience congestion collapse. Okay, but the important thing is the problem with effective. What's the problem with effective resource allocation mechanism? So what do you think? What's the problem with effective resource allocation mechanisms? So the effective utilization of the network is not the only criterion for judging a resource allocation mechanism. So number one, we need to take into consideration that effective utilization of network resources is not the only criterion. Is not the only criterion for judging a resource allocation mechanism. Right. So we must also consider the issue of issue of fairness. The second problem. The problem here is that a reservation-based resource allocation reservation-based resource allocation create controlled unfairness. Okay, so let me give you an example. Let's assume that with such a scheme, meaning the resource-based resource allocation, we have so we have two applications. So let's assume we have two applications using a link based on resource reservation. One application is a file transfer, and the other application is a multimedia application. Multimedia application. So a multimedia application is maybe utilizing 1 megabits per second across the link, whereas the file transfer application is only utilizing 10 kilobits per second. So two applications sharing a link based on reservation-based resource allocation mechanism, where one application is only making use of 10 kilobits per second, and the other application, say multimedia application, is making use of 1 megabits per second over the same link. Do you think it's a fair mechanism? Fair resource reservation mechanism? No, it's not, right? So that's why. So that's why. So that's why. So we would like for each flow to receive an equal share of the bandwidth, right? So we would like each flow to receive equal share. Okay. This means the file share application and multimedia application should be having equal share of the bandwidth, right? So this definition presumes that a fair share of bandwidth is that a fair share of the bandwidth means an equal share of the bandwidth. Right. And by the way, this covers our second evaluation criteria that was based on fair resource allocation. Right? So one evaluation criteria is effective resource allocation mechanism, and the second is the fair resource allocation mechanism, where we want to make sure that each application get a fair share of the bandwidth, means an equal bandwidth. And by the way, we also have a measure to calculate to see the fairness of a congestion control mechanism. So we can evaluate the fairness of end-to-end congestion control mechanism using Jaynes Fairness Index. Jaynes Fairness Index proposed by Raj Jain. Okay, so this after discussing this evaluation criteria of resource allocation mechanisms, it's time that we talk about the different resource allocation mechanisms, and for that we need to discuss, and this is the main topic of our discussion, by the way, we need to discuss different queuing disciplines. regardless how simple or sophisticated the rest of the resource allocation mechanism is, each router must implement each router must implement some queuing discipline. Right, and what this queuing discipline will do? This queuing discipline will govern how packets are buffered. And what do you mean by this? By saying packets are buffered means which packets get transmitted, which packets get transmitted. So by saying queuing discipline means queuing discipline governs how packets are buffered, means which packets get transmitted, and buffer space. It manages the buffer space. And what do you mean by this? This means which packets get discarded. So it's a very important decision that our queuing discipline has to make, that which packets will be discarded and which packets are buffered, means which packets get transmitted, right? And most importantly, queuing discipline is also directly affects the latency experience by a packet. It directly affects the latency. And what do you mean by this? This means that how long a packet waits to be retransmitted. So by the way, there are two common queuing algorithms that we'll talk about first. Two common queuing algorithms. Number one, first in, first out. First in, first out. And the second one is called fair queuing. FQ. Okay, so let's talk about the first one, that is first in, first out, is the most widely used queuing algorithm in the internet routers at the moment, right? So let's talk about the first mechanism, that is first in, first out. The idea of first in, first out is also called first come, first served. Means first come, first FCFS, first come, first served queuing. All right, so what we do basically here is that a router maintains a queue. And this queue has some finite space. And let's assume these are the packets in the queue waiting for the transmission. So the packets that have arrived first will be transmitted first. So this is the next packet to transmit. Next to transmit. And we can say this is the next pre-buffer. Next pre-buffer. And this part of the queue is representing the queued packets. And this part is representing the free buffer. Right, and if new packets comes in, it will be placed inside the queue depending on the available space. And if we assume that the queue is full, there is no space available in the queue. So what will happen then? What will happen with this arriving? So let's assume that this is the arriving. This is the arriving packet. Okay, so if note that if the queue is full, the router will discard this arriving packet. Why? Because there is not enough buffer in the space. By the way, this is called tail drop. Why? Because we have dropped a packet at the tail of the queue. Why? Because the queue was full. There was not enough space available in the buffers here, right? And remember that these are two different ideas. What? The tail drop, and first in, first out. First in, first out are two separable ideas. Why? Because this drop tail is a drop policy, where this drop policy is very simple in first in, first out. That is, if a queue is full, we'll drop the packet, right? And this first in, first out is a scheduling discipline. Is a scheduling discipline. Okay, so and usually the bundle is referred to simple first in, first out queuing, right? So when I say first in, first out, it means that a drop policy is already there. More precisely, it should more precisely be called first in, first out with a tail drop policy, right? Mechanism. Okay, but anyways, if we refer to a first in, first out, this means a tail drop policy is already there. By the way, this first in, first out with tail drop is the simplest of all the queuing algorithms and is the most widely used in the internet routers, as I discussed earlier. But important thing is that the prevalent form of congestion control in the internet currently assumes no help from the router. So this is very important to see. So if we look at this, the management of this queue, router is merely doing anything, merely helping the traditional congestion control algorithm in controlling the congestion, right? It's just queuing the packets, and if the buffer is full, the router will start dropping the packets. The router is not really helping the traditional congestion control mechanism in this congestion control in controlling the congestion in the network, right? So we can also propose some variations in this first in, first out queuing, and we call it priority queuing, or so first in, first out with priority queuing. With priority queuing. So here we maintain more than one queues. For example, this is one queue. This is another queue. Let's assume we have another queue. And the priority of this queue is 1. This is the highest priority, for example. Then we have the priority of this queue 2, and then the third queue has priority 3. And the router processor first will provide services to queue number 1. So the router process will not serve queue 2 until it is done transmitting all the packets in queue 1. So there are packets waiting in queue 2. There are packets waiting in queue 3. So what's the drawback of such a mechanism? I mean, what do you think was the problem with this priority FIFO with priority queuing? What's the problem? Yes, you're right. The problem is high priority queue can starve out all the other queues. Right. So where the router processor is, busy in serving queue 1, which is the highest priority queue, and the other queues are starved, means the packets are experiencing delays. There are timeout at the sender side. The sender is sending retransmitting the packets again. This will result into congestion. But there is an obvious implementation of such a mechanism of FIFO with priority queuing is the routing updates. So in order to update the routing tables at different routers, we send a special queue. We set a special queue for the priority packets of routing updates, right? And this, by the way, this implemented with the help of. So the example of such an implementation is routing updates. Right, and how we identify that a packet has the routing update, we use differentiated service code point in the type of service field of IP datagram, right? And this identifies that this are priority packets that need to be placed in a high priority queue for immediate transmission of the data. Okay, so so what's the problem with this? What do you think? What's the problem with first in, first out? What do you think? Yes, the problem with first in, first out is that it does not discriminate between the different network sources, between the different traffic sources. Okay, and then because of this, it is possible for an ill-behaved source or a flow to capture an arbitrarily large fraction of the network capacity, right? Let's assume that in this queue we have two types of application sending data. One is one application is using TCP's end-to-end congestion control, and the other application is using is based on, for example, is internet telephony. So if we are not discriminating, if the first in first out mechanism is not discriminating between the different flows, means between these two different types of application, so what will happen? So internet telephony based application will keep sending data to a router, regardless of the drop of arriving packets. This will not affect the sending rate of the internet telephony application. But on the other side, if we are using application based on TCP, so if a packet is dropped at the router, the sender will experience a timeout, a triple duplicate acknowledgement, and the sender will slow down the sending rate. So in this case, the application that is making use of TCP for its transmission will slow down the sending rate, whereas the internet telephony based application arbitrarily use the large fraction of the network capacity, right? So this is not a fair way to allocate the network resources, right? So that's why we need to talk about the second type of queuing mechanism or algorithm, which is called fair queuing. Right. So the idea of FQ is to maintain a separate queue, for each flow. Right? Currently being handled by the router, right? So the router oversees these, or the router observes or service these queues in a round robin fashion. So let's try to understand this with the help of an example. So let's assume that we have one queue here for one flow. Say, let's assume that this is flow number 1, and we have a queue for flow number 1. Then there is another queue for the second flow. So let's say this is flow number 2, and then we have a queue for the third flow, for flow number 3, and then we have a queue for the fourth flow, say flow number 4. And what a router does is that it serves these queues in a sort of round robin fashion. So what it does is it provides services to these queues in a round robin fashion. It's a round robin service, okay? Where the queue will first get a packet from flow 4, then it will get a packet from flow 3, then it will get a packet from flow 2, and then flow 1. So first of all, it will try to prevent flow to affect the transmission of the other flow. Now let's assume that let's assume the previous example that was creating a problem in first in first out queuing. So we have an internet application, or say internet telephony, and say the data of internet telephony is being placed in flow 1, and then we have an application making use of TCP, and the queue number 2 has been attached to this flow. So what if the internet telephony keeps sending on the data at a faster rate? So these are all the packets that are queued here. So this queue will become full, and the router will start dropping packets from this queue that is being reserved for internet telephony. But on the other side, this is not affecting the transmission of the application that is making use of TCP, because there is a separate flow here, and we are placing the packets of this TCP flow in this queue, right? So clearly, this will overflow the buffer of internet telephony, and the packets will the router will start dropping packet from this queue, but not affecting the transmission or the flows of flows placed in the other queue, right? So when a queue reaches a particular length, additional packets belong to that queue. That flows queue are discarded, which is the case in this internet telephony, right? So by the way, this works well with with an end-to-end congestion control mechanism. Why? Because it is implicitly telling that or controlling the congestion control in the network, right? Or sending feedback, implicit feedback to the end machines. So the advantage of air queuing is that it works well with an end-to-end congestion control mechanism. Right, but there are some complications, or there are certain things that we need to consider here. So there are certain complications here that we need to identify, and then we need to look at its solution. So the complications about the fair queuing is that packets are being the packets being processed at a router are not necessarily of the same length. So the first complication is packets being processed are not necessarily of the same length. What do you mean by this? So let's assume that a TCP application, that this flow that contains a packet from a TCP application has a size of 1,000 bytes, right? And the size of this internet telephony application, the packet size of this internet telephoning application is 500 bytes. So if in a round robin fashion, if a router takes one packet from this queue and one packet from this queue, what do you think? Is it a fair allocation of the bandwidth? No, it is not. Why? Because the packet size of these two queues, the packet size of these two queues is not the same, right? So if we want to truly allocate bandwidth in a fair manner, it is important to take packet length into consideration, right? So it is important, or it is necessary to take packet length into consideration. Okay. So what do you think? What is the solution of this complication or this problem? So we have identified a problem with the fair queuing, and now let's talk about its solution. The solution of this problem of variable packet lengths in different queues is to come up something similar to bit by bit bit by bit round robin. But the problem is, we just cannot do it. For example, this we just cannot interleave the bits from different packets. This means what? We just cannot do that. We take one bit from here, from this packet, and then again take one bit from this packet, and then we keep doing this. This is not possible, right? So the problem implementing a bit by round robin is that it's not feasible. It's not feasible to interleave the bits from different packets. So this means that the fair queuing algorithm has to simulate the behavior of bit by bit round robin. Okay, so it has to simulate the behavior of bit by bit round robin. How? By determining when a packet would finish being transmitting. So a router has to identify when it will finish transmitting a packet if it were being sent using bit by bit round robin, and then it can use this finishing time to sequence the packets for transmission. So the solution is, how we would simulate this is, we will calculate, a router calculates the finishing time of a packet. Finishing time of packets, and then this finishing time is used to sequence. The packets for transmission. Right. So this means we have to calculate the finishing time of a packet for a specific flow, and if the finishing time is expressed in terms of how many clock ticks it takes to transmit a packet, then we can calculate this time. So what I'm saying is, if the length of the packet is expressed in terms of how many clock ticks it takes to be transmitted. So we can calculate the finishing time. How? We can calculate the finishing time with this formula, where f of I is equal to Si plus Pi. Okay, where this Pi denote the length of packet I. Okay, and SI denote the time when when the router starts to transmit packet I, and this FI denotes the time when router finishes transmitting packet I. So we can calculate this Fi, which is the time when a router will start finishing packet I, and it depends upon it's basically sum of Si, which is the time when a router starts to transmit packet I, plus the Pi, which is the length of the packet I, right? But there is a question that we need to answer. The question is, what do you think? When do we start transmitting packet I? What do you think, students? When do we actually start transmitting a packet I? So the answer to this question depends that whether packet I arrived before or after router finished transmitting packet I minus 1, the earlier packet, right? So when do we have to start transmitting packet I? It first of all depends upon that a packet I arrived before or after the transmission of packet I minus 1 from this flow. If it was after, then the first bit of the packet I is transmitted immediately after the last bit of packet I minus 1. It's also possible, by the way. So this means the starting time depends upon its arrival time. Either it's arrived before the completion of the previous packet or after the completion of the previous packet. So this there's another possibility. It's also possible that the router finished transmitting the previous packet, which was packet I minus 1, long before I arrived. So there was a gap between the arrival of packet I and the completion of packet I minus 1, right? So if we let AI denote the time packet I arrives at the router. Then we can modify this SI, which is what? Which denotes the time when the packets, when the router starts transmitting packet I, right? So we can modify, so we can say SI now is either maximum of FI minus 1. So this was the time when the router has finished transmitting the previous packet, which is I minus 1, or A I, which denotes the time when the packet I arrives at the router. So thus we can modify our original equation that is used to calculate Fi, which is the finishing time of packet I. Now the finishing time of packet I is maximum of Fi minus 1, the finishing time of packet I minus 1, the previous packet, or the arrival time of packet I plus the length of packet I, right? So for every flow, we calculate this Fi, and it means for every flow, we calculate Fi for each packet using the above formula, right? We're using this formula, right? And Fi is treated as timestamp, so this is very important. So this Fi is treated as timestamp. Right. And by the way, this timestamp is used to sequence the transmission of the packet, right? So this means a packet with lowest timestamp will be transmitted first, right? So we use Fi to calculate a timestamp, and then we use this timestamp to sequence the transmission of the packet. So this timestamp is used to sequence transmission packets. Of packets. So I'd like to understand that how we use this timestamp to sequence the transmission of packets. So let's assume that we have a queue to monitor flow from one application. So this is queue number 1, and it is for, say, flow number 1. And it has 2 packets where one has the finishing time 5, and the other has, so the F is 8. Okay, and then we have another flow. This is flow number 2, and its F value is 10, right? And then this is the output link representing the transmission of this packet. So let's assume that this represents the packets from flow 1, and this color here represents the packet from flow 2. So what do you think, which flow will be first transmitted? What do you think, which packet will be first transmitted? Yes, you're right. So we will transmit first packets from the flow number 1. Why? Because their finishing time is less as compared to the packet from flow 2, right? So we will first, on this output link, we'll first put the packets from, will first sequence the packet from flow 1y because of their timestamp value, right? So we will then place, after placing the two packets from this flow 1, will get a packet from the flow 2y because it is based on the actual the completion time of the packets in flow 2. But there is also a problem with the fair queuing, that it does not consider this timestamp option while it is transmitting a packet from a queue, from a flow. So let's try to understand this. So let's assume that here we have flow 1, and in flow 1, a packet that has a finishing time, say 2, is arriving. So a packet is arriving. Okay, and then we have another flow number 2, queue for flow number 2, where a packet is in placed, and this represents the packet off. And obviously the timestamp or the finishing time of this packet is greater than the packet arriving in flow 1. Now, what will happen? What do you think? What will happen on this output link? Which packet? So this, please note that it is transmitting. So what will happen? Yes, in this case, the router will first put F10, and then, the packet from the flow 2, and then it will place sequence packet from flow 1. Why? Because it was transmitting when a packet in flow 1 has started arriving. So the fair queuing does not take into consideration the scenario where of this timestamp, where in a scenario where a packet is already being transmitting on the output link. Okay, so what are the advantages of, what do you think, what is the advantage of fair queuing? Yes, number one, it's important to note that FQ, fair queuing, is work conserving. What do you mean by work conserving? This means that using fair queuing, a router will always transmit something on the network as far as there is a packet in a queue to be transmitted. The second advantage is it provides a guaranteed minimum share of the bandwidth to each flow. It provides guaranteed minimum share of the bandwidth to each flow, as we have seen in this and previous examples. By the way, there are also different variations of fair queuing, such as weighted fair queuing, where we assign a weight. Where we assign a weight with each of these flow to select the specific number of packets from each flow, and then provide services to the other flow.